As we've seen, the Arrhenius equation provides us a really convenient way to capture the temperature dependence of the rate constant. But it is an approximate equation, and it is derived basically from empirical observations, so it doesn't give us the same level of detail that we may want to get if we want to try to predict what the reaction rate might be for a given reaction. Granted, we're a long way from being able to do that. However, let's take a look at some other ways that we can formulate reactions that might give us a little bit more insight. So for this, I want to focus on reactions that have the general form where there's two molecules that are going to collide together, and this leads to products. All right, now what we're going to do is look at this from the perspective of a collision model, which means that we're really interested in how frequently these two molecules collide. Do they have sufficient energy to activate a reaction? Are they colliding in the right orientation to make that reaction happen? Now I'll remind you that not too long ago, an earlier lesson, we derived an expression for the collision frequency between two molecules A and B, and it looks something like this. We had first a product of a area, which is basically a collisional cross-section for A and B, and we'll talk about that in just a moment, times the average relative velocity of these two molecules in the gas phase, times their number densities. All right, so it's a nice compact expression that gives us some idea about the collision frequency between A and B. So let's talk about each of these. Okay, as I mentioned, this sigma AB is a cross-sectional area. And if you'll recall, when we were talking about the collision frequency and then mean free path and time between collisions and things like that, we would model these particles, for example, as spheres, and then we could, for example, for each of these, for example, for A, I might have a cross-sectional area that would be pi times the diameter of A squared. So it's like the area of the circle that would be cutting through that sphere. When we have two of them, a more appropriate one might look something like this. Doesn't have to, but this would be if we modeled our things as spheres. It would be pi times the average of the two diameters, so over 2 squared. Okay. This is, I don't specify that this is exactly how we define this cross-sectional area because, frankly, molecules have all kinds of shapes, and so this may not be an appropriate way to catalog the shape of this molecule. Now, we also have these two factors, rho A and rho B, and those are basically the number densities of each of these molecules. And just to remind you, they're defined, for example, rho A would be the number of A molecules divided by the volume, and similarly for molecule B and rho B. All right, so in effect, they're a stand-in for the concentration of these particles. Now, the last one, and it's one I'm going to set over here, this relative velocity between A and B, is something that we could write using the average velocity for molecules in the gas phase. So this is what the expression looks like. So it looks an awful lot like the average velocity expression. The one difference, though, is instead of the mass of a particle, we're going to use the reduced mass. And it turns out that this accounts for the relative part of these velocities. And this is, of course, the square root. So this is actually going to be the one of these factors that has some temperature dependence. These other two, the rho, the number densities, and the sigma, these are just qualities of this particular system and are not temperature dependent, but this one is. Okay, so we have already then built in some temperature dependence here, but we're missing some other critical factors that will that we'll need in order to relate this to a reaction rate. Now, one of the things I'd like to do is pause for just a moment and make sure that these factors make sense. Okay, so what we're basically saying is that collision frequency is going to depend on these factors, and it will be larger if the cross-sectional area is larger, okay, well that makes sense. Larger molecules are going to collide more frequently. So if sigma is larger, they should collide more frequently. It also is going to say that the frequency is larger if the molecules move faster. So if they have a higher average velocity. And that also makes sense. The faster things are moving, the more often they're going to run into each other. And it will also be greater if the molecules have greater concentration. So in other words, if there's more of them around. And going back to an analogy we used earlier, if you're walking down the street and you're thinking about how many times will you collide with other people who are walking down the street, if the other people are bigger, you'll collide with them more often. If they're moving faster, you will collide with them more often. And if there are more of them, if there are a greater concentration of people, you will collide with them more often. So all of these, I think, I'm going to just put the sign of approval. These all make sense. All right, so why shouldn't we just plug this in and say this is equal to the rate? Well, there's two factors that are missing, and I'll remind you of those. One is that we need to have sufficient energy to activate the reaction. Okay, we haven't got anything in this collision frequency that accounts for that. The second thing that we don't have is the proper orientation. In other words, when molecules hit each other, and if they're small enough, then it doesn't really matter how they're oriented. But if they're larger, then you want them to hit on the end that's going to undergo the reaction. So if it doesn't have that proper orientation, not all collisions will end up being reactive collisions. All right, so if we want to account for that, one way we can do that is by introducing, and I'll call it an arbitrary factor, but I'll call it P sub collision. This basically is the fraction of molecules, or fraction of collisions with the right orientation. Okay, so P call is going to be a number between 0 and 1, so it's a fraction. Maybe I should have made it an F, but this fraction is going to correct for this so that we're not overcounting the collisions. If we have collisions that don't have the proper orientation, they aren't going to react. So what it means then is that we can now begin to put these things together to construct something that looks like a rate expression. So let's write that down. So I want to have something that is a rate. How am I going to put this together? Well, it's intrinsically going to be equal to this collision frequency, okay, because collisions have to happen in order for a reaction to happen, times the fraction of those collisions that result in a reaction. So that'll be something less than 1. And then for this sufficient energy to activate, we already have a correction factor for that from the Arrhenius equation. We can just use the same one. This will cover that. So now we can basically relate the rate of a reaction to these three factors multiplied by one another. And when we write all of this out, I'm going to reorder them a little bit. We'll have P call, and I'm going to write out ZAB because I want to focus on the different parts of this. So we'll have 8 kBt over pi times mu AB to the 1/2, and we'll have e to the minus a EA over RT times rho A rho B. Okay, now having written it out this way in all of its glory, we can begin to look at the various components of this and interpret them in useful ways. First of all, I'll note that all of this stuff here is stuff that we can relate now to our frequency factor. And I'm going to explicitly note that it is a function of temperature because of the temperature that appears right here. Then we have the Arrhenius factor with the activation energy, and then these two factors here basically are proxies for the product of the concentrations of A and B. So when we put this together, what we're really saying is that this factor times the Arrhenius factor is what constitutes our rate constant for the reaction. So we're going to have, again, this factor that accounts for the fraction of collisions that are reactive, the cross-section of the molecules, their average relative velocity, and the Arrhenius factor. All right, so this is how we can now, and got things a little bit too close there, this is how we can define our rate constant now as a function of temperature. And I want you to notice that this rate constant now, its temperature dependence is t to the 1/2 e to the minus ea over RT. So it's a little bit more nuanced than simply using the Arrhenius equation where we assumed that the frequency factor was a constant. It now has some temperature dependence. This is much weaker temperature dependence than the temperature dependence that comes out of this exponential factor. So that's why it doesn't show up sometimes in a large number of reactions, because it's just not exerting very much control or very much effect on the rate constant. All right, now this would be a perfectly good way to formulate our reaction rates and certainly provide some predictive ability for gas phase reactions. I will say the one weak factor in all of this is this factor here. P-call is a factor that is important because we know not all collisions are going to be oriented properly, but it's really difficult to predict or to evaluate. So for that reason, we may want something that is a little bit more satisfactory for formulating our rate laws.